Hello, students. How are you? Good. I'm fine too. So, today we are going to continue the topic of measures of position. Today we'll discuss geometric and harmonic mean. We will learn how to use them, how to compute them, how to interpret them. Let's start. First goes geometric mean. Geometric mean is an alternative measure to an arithmetic mean, which can be simultaneously used and can be treated as a supplement to our considerations about the average level of indicated phenomenon. We denote geometric mean by the following formula, in which we have the symbol of geometric mean: x with a underscore, horizontal line, and here we have capital G letter, which indicates that we deal with geometric mean. Geometric mean is a nth root of a product of all the values of our variable. In other words, it means that we compute the product of all variable values. We multiply all the variable values by ourselves, and after that we compute n root of this product. N is a population size, the number of variable values. The features of geometric mean are following. We usually use a geometric mean when we want to express the average dynamics of different phenomena. Because geometric mean is more resistant to extreme observations, extreme high or extreme low. Let's imagine following situation. We investigate the changes of a fake economic variable. These changes can be expressed in percents. So, for example, in the first year, our fake variable raised by 1%, in second year by 2%, and in the third year by 1000%. So we can compute arithmetic mean and we can compute geometric mean. Arithmetic mean will be 1 plus 2 plus 1000 divided by 3. And what we have here, 1003 divided by 3 is 334.3%, of course, approximately. We can also compute geometric mean, and what we have here, cube root of what? 1 multiplied by 2 multiplied by 1000. And what we have here, 1 by 2 by 1000, it's a cube root of 2000 2000s. and we have here 12.6%. Yeah, so the difference between these means are huge. Yeah, so here we have an extreme huge observation, abnormal observation. Yeah, and we see that geometric mean is more resistant to this kind of situation. Here we have overestimated average growth tempo in following years. Okay, but we have to be careful. Why? Because we can't always compute a root of something. Yeah, there exist some conditions in which we can compute a root of something. We have to pay attention to the population size, so the degree of a root, and we have to pay attention to the sign of this product. So if it is positive or if it is negative. And this geometric mean can be calculated if and only if population size is odd. You know, odd numbers. 1, 3, 5, 7, and etc. So if the population size is odd, is okay. We can always compute our geometric mean. Yeah, for example, -3, 3, and 3. Geometric mean will be -3 by 3 by 3 and cube root of this kind of product. And we have cube root of -27, which is -3. It's okay, yeah? The product is negative, but the population size is odd and everything is okay. Yeah? Alright. But if population size is even, you know, even numbers, 2, 4, 6, 8, etc. Yeah, we are talking about the population size, even population size. The product of the variable values must be non-negative. Yeah, we can't compute the root of a negative product. Yes, if the population size is even. So our product must be non-negative. So it means we can have here 0 and positive numbers only. A simple example. Let's imagine following individual series, -3 and 3. Yeah, the product of these two values is -3 by 3 is -9. We can't compute a square root of -9. It is impossible. Yeah, so in that situation we can't compute geometric mean. But if we have here, for example, 3 and another 3, yeah, minus 3 maybe. We have 2 minus 3 and 2 3 numbers. And in that situation we have what? Geometric mean is equal to 4th degree root, yes, of minus 3 by minus 3 by 3 by 3, and it's 4th root of 81. Yeah, and this is of course 3. So the product is positive, the population size is even, so we are able to compute a geometric mean. And the last one feature that I must stress here, average logarithm, natural logarithm of the variable values. Yes, so here we have x1, x2, and so on up to xn, and we compute a logarithm of these values. So logarithm of x1, logarithm of x2, and so on, logarithm of xn, and we can compute an average logarithm. Yeah, average logarithm, which can be denoted by this symbol, average logarithm of the variable values. This is the sum from I equal 1 up to n of logarithm of xi divided by n. Yeah, it's a logarithm x1 plus logarithm x2 plus logarithm xn divided by n. This is average logarithm of the variable values. This category equals this category, logarithm of the geometric mean. Yeah, so it also means that here we have Euler constant, yeah, in the basis of the logarithm. So it means that Euler's constant to the power of average logarithm of the variable values gives us geometric mean. This is very interesting feature. We can prove the truth of the last feature of geometric mean. Let's start with the right side of this equation. Let's expand this. Logarithm of geometric mean is the right side of the equation, and it equals what? It's a logarithm. It's a logarithm of nth root of the product from I equal to 1 up to n of xi values. We can denote it using exponent. So this is a logarithm of the product from I equal 1 up to n of xi. to the power of 1 over n. Yeah? The same thing, but different notation. This is logarithm. So I can move the exponent before the logarithm. Yeah? Well-known feature, logarithm of a to the power of b, it can be denoted, can be written down like this: b multiplied by logarithm of a. Yeah, very simply feature known from high school, for example. 1 divided by n, logarithm of the product from I equal 1 up to n of xi. And another feature of the logarithm we will use logarithm of the product. For example, logarithm of the product of a and b is a sum of the logarithm. Logarithm a plus logarithm b. Yeah? Logarithm of the product is the sum of logarithms. So here we have what? 1 over n, and here we have logarithm of the product. So we can write it down using the sum. Is the sum from I equal 1 up to n of what? The sum of logarithm, the sum, especially the sum of the logarithm of variable values. And this is finally this is simple average logarithm of x variable values. Let's do the first exercise connected with the geometric mean. We have a certain economic variable in the years 2009 and 2016, and we see its tempo of change. Here we have our fake variable, which is the tempo of change expressed by the appropriate index, which express year-to-year change, percent change of considered economic variable. So we don't see the level of our variable, yeah, we see only the changes, and that changes are expressed by the following index. First value 1.009 means that in 2009 the value of our variable was 0.9% higher in comparison with the previous year, compared to the previous year 2008. So in other words, in 2009 our certain economic variable increased by 0.9% compared to the 2008 year. Okay. Maybe we should interpret this value from 2012 year, 0.9%. 8. So it means that the value of economic variable in 2012 was 2% lower than in 2011 year. And we see here year by year changes of our economic variable, but we need a synthetic measure, an average change expressed in percents, an average change in this period of 2009 and 2016. As we have here a lots of value, we need a one synthetic value which express an average yearly change of economic variable. We can use a geometric mean here, yeah? So, in order to compute a geometric mean, we need the product of all values. Therefore, we multiply all the values from that column in order to compute a geometric mean. So, geometric mean is equal to the root. Yeah, we should determine the degree of the root. It depends on the population size. Yeah, how many observations we have? 1, 2, 3, 4, 5, 6, 7, 8. Yes, we have 8 values, so we have 8 degree of our root. Yeah, and we start to multiply all the values from that column. So first 1.009 multiplied by 1.007, the next value, yes, multiplied by 3 dots, and the last value is 0.99. Yeah. Okay, so now we take calculator and we multiply all the values. 1.009 multiplied by 1.007 multiplied by 1013, and so on and so on. And here I have the partial results, and the product of all values equals to 1.0524. Yes, this is the product of all values of considered economic variable, the tempo of change of the economic variable. Yeah. So geometric mean is a 1.0524 to the power of 1 over 8. Yeah, 1.0524 rise to the power 1 over 8. it is approximately, well, 1.0064. Let's try to interpret this geometric mean. So this is an average yearly tempo of change of a certain economic variable in the period of 2009-2016. Yeah, so we can write down this average tempo of change of considered variable is about 0.64% per year. This is one version of the interpretation. Another, year by year, the values of economic variable increased on average by 0.64%. We can also compute successfully a geometric mean in the frequency distribution series. The only things that we need are the middle of the classes in the interval series and the values of considered variable in related to a point series. Of course, we can perceive in the as the exponent here frequencies and relative frequencies. They play a role of weights, similarly to the previous situation when we talked about the arithmetic mean. So, on the basis of this information, we can compute the first example. The table below shows the percentage of selected countries in the world characterized by positive annual real GDP growth in 2017. Here we have considered variable growth rate, which is expressed in percents. It can be denoted as xi. Here we have the percentage of countries which are characterized by the next growth rate tempo of GDP. So, first value, almost 26% of countries are characterized by GDP growth rate from 0.1 up to 2% per year. Yeah? And now we are going to calculate and interpret arithmetic mean and geometric mean of the GDP growth rate in selected countries of the world, which are characterized by the positive growth tempo of GDP. Here we have the column with relative frequencies. So we are going to use this version of our formula in order to compute geometric mean. So what do we need here? We need the column with the middle of the classes. Yes, xi with a circle, the middle of the classes. So this is the value that is placed exactly in the middle between upper and lower bound of each of the class. So first middle of the class is 1.05 because it is 2.0 plus 0.1. It yields 2.1 divided by 2 gives us 1.05. And the next 6.1 divided by 2 is 3.05, and so on, 5.05, 7.85. Okay, we have the column which is titled the middle of the classes. Okay, and after that we are going outside our formula. We should raise the middle of the classes to the power of fi's. Yeah? So in the first column we have what? Xi to the power of fi. 1.05 to the power of 0.259. So as you can see, we need a scientific calculator. 1.05 to the power of 0.259, and the result is approximately 1.013. Yeah. Next row, 3.05 to the power of 0.38. 3.05 to the power of 0.38, and it is approximately 1.528, and so on and so on. 1.367 and 1.414. Yeah. The scientific calculator is needed here. And now we are able to compute the product of these values. Yeah, the product of the values that we find in this column. So 1.013 1.013 multiplied by 1.528 multiplied by 1.367 and multiplied by 1.414. Yeah, and the final result, the product of the middle of the classes raised to the power of fi's is about 2.992. 2.992. This is average annual growth rate of GDP in selected countries. So, geometric mean is the product from I equal 1 up to 4, because we have 4 classes of xi with a circle. The middle of the classes rise to the power of fi's, and the final result is 2.992%. So it means that average, this is the interpretation, average annual GDP growth rate in selected countries in 2017 was about 2.992%, and that's all. Yeah, average annual GDP growth rate in selected countries in 2017 was about 3%. Yeah. We can also compute here arithmetic mean, as we can treat this like an exercise, a kind of revision, reminder. We know that arithmetic mean is the sum from I equal 1 up to k of xi with a circle, the middle of the classes, multiplied by relative frequencies. So, in order to compute arithmetic mean, we need this kind of column. The middle of the classes multiplied by relative frequencies. And we will be able to compute arithmetic mean, and after that we will make a comparison between geometric mean and arithmetic mean. Let's back to the column of the product of the middle of the classes and relative frequencies. So in first row we multiply what? 1.05 by 0.259, and the result is about 0.272. In the next row, here we have the product of 3.05 multiplied by 0.38. and the result is 1.159. And so on. We have following values in that column: 0.975 and finally 1.319. And as you can see here, now we are going to sum up that column. So thus we have here what? 0.272 plus 1.159 plus 0.975 plus 1.319, and the final result is 3.725, and this is our arithmetic mean of real GDP growth rate in selected countries. The sum from I equal 1 up to 4 from the product. In product we have the sum of products. In the products we have the middle of the classes and relative frequencies, and the result is 3.725%. And the interpretation is similar, yeah, but we know that here we have measured average GDP growth rate using arithmetic mean. Here we have measured average GDP growth rate using geometric mean, yeah. And as you can see, average GDP growth rate using arithmetic mean is significantly higher than analogous measure measured by geometric mean. Okay. Now we can move on to the harmonic mean, the last example of measures of position. Harmonic mean is a very specific measure. As you can see, this is the ratio, ratio between the population size in the individual areas and the sum of the reciprocal values of considered variable. We denote harmonic mean using X with underscore. H letter indicates us that we deal with a harmonic mean. Population size, the sum of the reciprocal values of the variable. We usually use the harmonic mean when we want to express the average, a typical value of the ratio variables. You know, the speed is an example of ratio variable, kilometers per hour. Next example, GDP per capita, and so on. So harmonic mean is especially dedicated to the ratio variables because it works well here, in the expression of the typical a value of considered phenomenon. We divide something by something, so we have to remember the following rules. The harmonic mean cannot be counted in two cases. First case, when at last one of the variable values is equal to 0. So when only one value is equal to 0, we can divide 1 by 0, so we are not able to compute harmonic mean. And the second situation is when the sum of the reciprocal values of the variable is equal to 0. So in this situation, the whole sum is 0, so we can't divide n by 0. We are not able to compute harmonic mean. We can also find ourselves in the situation when we shouldn't use the harmonic mean. This kind of situation is when one variable value is close to 0. Let's imagine following situation. We have this kind of individual series. 1, 1, and 1 millionth. Yeah? So arithmetic mean will be somewhere between 1 millionth and 1. Yeah, but the harmonic mean will be much higher because reciprocal values are following. 1, it's 1. 1, and here we have 1 million. Yeah? So the closer to 0 we are, the higher value, reciprocal value we have. Yeah? And in that kind of situation, our considerations are distorted. So in case of variable values close to 0, we shouldn't use the harmonic mean. Of course, we can also find the situation when several values are close to 0, and the situation when the whole sum is close to 0. Yeah, in that cases we shouldn't use the harmonic mean. Let's make an example of the harmonic mean computation. The police speed camera measured the speed of 9 cars which exceeded the speed limit on the given day. The results are summarized in the table below. Yeah, here we have considered variable xi and its values. We have 9 observations, 9 values, and let's try to compute the harmonic mean. Our variable has a ratio character. Yes, it's a speed where we measure kilometers per hour. Yeah, so harmonic mean is appropriate measure of average level of considered phenomenon. Here we have an advice on the appropriate accuracy for places after a dot. We can utilize this formula because we deal with the individual series. So first we need the reciprocal values of our variable. 1 divided by, here we have 1 divided by xi, so it means in the first row we should divide 1 by 61, and we have what? 1 divided by 61, it is approximately 0.0164. Next step, in the next row we have 1 divided by 75, and we have 0.0133. 4 places after a dot. I ensure this kind of approximation, and next values are following: 0.0137. Yeah, remember that in the table we write only the final results. Computations are not necessary here. And the next one, 0.0101, and so on. The last value is 0.0112. Yeah, this is a consequence of dividing 1 by 89. And in the next step, we need the sum from I equal 1 up to n. Here, and the population size is 9. It means that we sum up 9 elements, and then the sum of these reciprocals is 0.1147. And now we are able to estimate the harmonic mean. Harmonic mean is equal to n, the population size in the numerator, 9, divided by denominator. Here we have our sum that we have computed, 0.1147, and 9 divided by 0.1147 is about 78.466 kilometers per hour. This is an average speed of cars which exceeded the speed limit. So we can write it down. Average speed of the cars which exceeded the speed limit was about approximately 78.5 kilometers per hour. Yeah. So now we know a typical level of investigated phenomenon, average speed of the cars. Of course, we can also compute other means, arithmetic and geometric mean. The results will be following. Arithmetic mean is about 82.111 and geometric mean is about 80.147, of course, kilometers per hour. So I encourage you to check it out if it is true. Good luck. Now we need to work a little on the frequency distribution series. Here we see some formulas that are needed in the harmonic mean computation. We see a group of formulas appropriate for in the interval series and appropriate for the related to a point series. We see also another division into a group of the formulas using the frequencies and using the relative frequencies. The worth noting fact is here in the nominator. When we use our frequencies, we have the population size. When we use our relative frequencies in the nominator, we have one value. Another difference is hidden here. Ni frequency turns into relative frequency. This is the only difference. Okay, so I will show you how it looks like in the practice. Task 7. The task that summarizes today's considerations, because the command is calculate the arithmetic, the harmonic and geometric mean. Here we focus on, at the moment, on harmonic mean. XYZ's management has compiled a table showing the BMI index of its office workers as at the end of 2018. What is your BMI index? I must stress that I meet healthy standards, barely but I do. Okay, so let's start to compute a harmonic mean of BMI index of these workers. BMI index is a kind of ratio variable, yes, because we divide the weight of a person by its height, yeah? Weight by height. Weight is expressed in kilograms, for example, and height is expressed in meters but squared. Yeah, this is a specific construction of this index. First goes harmonic mean. We will use this formula. What we need here? We need what? In the first step, NI's, yes, we see the frequencies here, NI divided by the middle of the classes. Okay, but before that, we should answer the question, how many people work in the firm? So we have to summarize the column of NI, yeah? Oh, sorry. The sum from I equal 1 up to 5, because K here is equal to 5, we have 5 intervals of BMI index. The sum from I equal 1 up to 5 of NI, so we sum up all the frequencies, is of course the population size. The population size here equals to 6 plus 45 plus 17 plus 12 plus 1, 81 office workers. This is the population size. Okay. Second step. In the second step, we should compute the middle of the classes, the middle of the intervals, xi with a circle. So here 10 plus 18 and a half, 25 and a half divided by 2, 14.25. Another middle of the class is 19 plus 24 and a half, 19 plus 24 half, 43.5 divided by 2, 21.75, and so on. I have a cheat sheet here. 27.25, 32.25, and 37.5. Yeah. Here we have all the middle of the classes. All right. Now we have a ratio between the frequencies and the middle of the classes. So we divide frequencies by middle of the classes. Here we have what? 6 divided by 14.25. Yeah, 6 divided by 14.25, and it is approximately, maybe let's assume that the accuracy is 3 places after a dot. It's about 0.421. 421. In the second interval, in the second class, we have 45 divided by 2175, and it yields 45 divided by 2175, 2.069, and so on. And so on. We have what? 0.624, yeah, 0.372, and at the end 0.027, yeah. All right. Now we are able to estimate the sum of that column, yeah, the sum of this kind of ratios. So, and then 0.421 plus 2.069 plus 0.624 plus 0.372 plus 0.027, and the sum is 3.513. 513. Yeah, exactly. So finally we can compute the harmonic mean. The harmonic mean equals to, and the population size. Here, population size is 81. Population counts 81 statistical units. 81. 81 divided by the sum that we have computed earlier. 3.513. Yeah, 81 divided by 3.513 is about 23.057 kilograms per meter square. Yes, this is the average BMI index of the office workers, yeah, in the XYZ company. Yeah, this is average BMI index of the workers of XYZ company and this average BMI index of the workers of XYZ company was equal to approximately 23 kilograms per meter square. Yeah, so it meets a healthy standards. Yeah, the upper bound of healthy standards of BMI is 24.5. Yes, so we are within the healthy standards of the BMI index. So is there any concerns about the health of the workers? No, everything is okay because we meet healthy standards here. Okay, let's compute other types of the mean. First goes arithmetic mean. In the arithmetic mean computation, we will use this kind of formula. We have computed the middle of the classes, so it's okay. It's necessary to compute the middle of the classes. We have done it, and in the second step, we need to compute the product of the middle of the classes and the frequencies. Yeah, so we multiply xi with a circle by ni. Yeah, in each of the row. So here we have what? 6 times 14.25. Yeah, 6 by 14.25. The result is 85.5. In the second row we have 45 times 21.75. 45 by 21.75. The result is 978.75. Yeah. Okay. Another column. Another row. 17 multiplied by 27.25. 463.25. 12 by 32.25. 387 and 37.5, because one we have here 1 times 37.5 point. Okay, and now we should compute the sum of these products, and the results are following: 85.5 plus 978.75 plus 463.25 plus 387 plus 37.5, and the final result is 1952. Yeah, 52. It's not necessary to sum up the column of the middle of the classes. It has no sense. Yeah, but we need exactly this sum. Arithmetic mean will be the sum that we have computed earlier, 1952 divided by n, the population size. The population size is 81. This divided by 81 gives us approximately 24.099. 24.099. And the interpretation is the same. This is the average BMI index of the office workers, but here measured using, of course, the arithmetic mean. Okay, and the last one. Geometric mean. Geometric mean. We need to use that formula, in which we have the middle of the classes. It's okay, yeah, because here we still have the column of the middle of the classes, and now we need what? Ni divided by n. Every ni for each of I equal to 1, 2, up to k, n I divided by n gives us simple relative frequency. Yeah, so the modification of that formula is the middle of the class to the power of the relative frequency. Ni divided by n gives us relative frequency. So we need the column with the relative frequency. So we can delete this column, and we are interested in the column of the relative frequencies. First relative frequency is Ni by n. So N1 here, N1 divided by n, it means 6 divided by 81. 6 divided by 81 gives us approximately 0.074. In the next row we have 45 divided by 81, and it's about 0.556. In the next row we have 17 divided by 81, 0.20, actually 210. Yeah, and here we have what? 12 divided by 81, 0.148, and 1 divided by 81 is 0.012. And of course the sum of that column is equal to 1, because the sum from I equal 1 up to k of the relative frequencies always equal 1. Yes, because here we see the structure of the population. Yeah, and the sum of all percentages is always equal to 1. We see that the most of the workers are characterized by the BMI index from 19 to 24 and a half. Okay, in the next step we will raise xi with a circle, the middle of the classes, to the power of fi. xi to the power of fi. xi with a circle, of course. So in the first row we have 14.25 to the power of 0.074. So we need the scientific calculator. 14.25 to the power of 0.074. And this is about 1.217. In the next step, we rise 21.75 to the power of 0.556. The result is 5.542. In the next step, we have 27.25 rise to the power of 0.021. 2.002. 32.25 to the power of 0.148. 1.672. And in the last row we rise this value to the power of this value. 37.5 and a half to the power of 0.012. 1.044. Yeah? Okay. And now we need the product. Yes? Earlier we operate by the operator of the sum. Here we have the operator of the product. So we need to multiply all the values that are placed in that column. So we multiply here 1.217 by 5.542 by 2.002 by 1.672 by 1.044, and the result is 23.57. Yeah? Finally, fortunately, we have approached the end of the task. Geometric mean is the product from I equal 1 up to 5 of the middle of the classes rise to the power of fi's, and the final result is about 23.57 kilograms divided by meters square. Okay, and the interpretation is the same, yeah, but we know that this typical level of investigated phenomenon were measured by the geometric mean. Okay, so that's all for today. Thank you. Bye.